Resonance. Okay. Resonance and resonance structures and exceptions to the octet rule. So we're gonna address resonance first. Resonance occurs when there's more than one possible solution that is correct to a Lewis dot structure. And so it's kind of hard to understand until we get into it. This is an example of resonance. And so what we're going to do is we're going to take a few minutes. I'm going to show you how we draw that and how we came up with that. And then we'll explain what it really means. So I'm just going to kind of focus in on this section here. We're going to still do the N, A, S, and U format. It's a NO3 -1 molecule. That's written up here. It's the NO3, it's the nitrate ion. So I have 1 nitrogen and 3 oxygens, so my needed would be 8 plus 8 plus 8 plus 8. I have 4 different atoms. 4 of those gives me 32. Okay, so if you weren't up on that the other day, maybe this will help a little bit. My available is the number of valence electrons. Nitrogen, the column, all the elements in that family have 5 valence electrons. And each of the oxygens have 6. And then remember, if it has a charge, and this one has a -1 charge, if it has a charge, this is where we factor that in. If it's negative, it gained an extra electron. So our total would be 18 plus 5 is 23 plus 1 is 24. This, remember, is N minus A, which would be 32 minus 24. So it's going to have 8 shared electrons. My unshared is A minus S, which is 24 minus 8. And yes, I heard somebody say 16. So this, at this point, should be familiar on how to do that. I know some of you are kind of skipping by that and doing things your own way, but we need to be a little bit careful because a lot of times it's not turning out right. So how do we draw that? Well, that's what I left this box here. Now you can't fill up the whole box because we're going to actually draw all 3 of these inside this box. It's a little bit of a squeeze, but I think we can do it. So nitrogen's in the middle. And I'm going to do it a little bit different from theirs. I'm just going to put an oxygen on top, oxygen on the bottom, and 1 to the side. Okay? So it says that we share 8 electrons. So 2, 4, 6. I got 2 more to go, so I'm going to go ahead and put the double bond on that oxygen. Okay? I've got the double bond on that oxygen. I could have put it on any one of these. I just picked that one arbitrarily for right now. Okay? And then I have 16 unshared. 2, 4, 6, 8, 10, 12, 14, 16. So that's a Lewis dot structure for a nitrate ion. Notice, and I want us to start focusing on that, when I have 3 sets of lone pairs, I put them on each side. When I have 2 sets, I put them kind of at an angle, and that's because we want to start representing that electrons do not like to be next to each other. So we really want these gaps here to be about the same. This is about a third, a third, a third. That's the proper way to do it. Okay, so I want you to start working on that. Well, why does the double bond belong on this one? Why don't we put it on this one? Or why don't we put it on this one? Why does that one get favoritism, right? So, well, let's do it with a different one. Let's do the double bond on the top. And then again, fill that in. So this is possible. This is possible, right? I mean, either one of those is possible. Well, then let's write the other one that's possible. That would be the double bond on the bottom. And in reality, we're supposed to put square brackets around these. I know we don't have much room to fit all this in. Because if they have a charge, we're supposed to write the square bracket and put the negative sign just outside the square bracket. So that would be the proper way to write all three. And when they're resonance structures, then what you do is you put a double-headed arrow between them, showing that really all three are possible. Each of those is possible. So I'll give you a second, let you get that drawn and caught up before I show you the next thing here. Okay, you there yet? So, this is what you're going to be doing in the lab. You're going to be building these molecules. This is an example of the nitrate ion. You have 3 oxygens. 2 of them have a single bond. If I turn this one, you can see this one has a double bond to it. So the question is this one correct? Is this one correct? Or is this one correct? They're all correct. And so in reality, the reason we show them this way is this extra pair of electrons, and it's kind of hard to see because of this double bond here. This extra pair of electrons doesn't only belong to this oxygen. It also belongs to this one and to this one. Remember, this is all an electron cloud, right? They're not in specific places in the atom. So these 2 extra electrons spend part of their time here, they spend part of their time here, and they spend part of their time here. They're moving around to all 3 different spots. They don't belong to any one of these, they belong to all 3. Okay? So the only way we can show that is with this type of format. So that's what we mean by resonance. This double bond does not belong to this one, it belongs to all 3. They keep moving around. Because electrons never are still anywhere. They're always in constant motion. So I want you now, we have an example for the carbonate ion, CO3 with a -2. I want you to draw that one. Okay, I want you to take a minute and I want you to draw that one. Okay, so it really was almost identical to the other one, wasn't it? Because you still had your N still was 32. On your A, this was a 4, 6, 6, 6, but this was a 2, so you still ended up with 24. So it's really set up the exact same way. Are we somewhat okay with the resonance structures then? I mean, we can take a little bit more time, but